All right, good morning again. This is Mr. Ainsworth. We're in part 2 of lesson 17 on the washer method. We're going to take a look at 3 more examples to illustrate how to use the washer technique to find the volume of a solid at revolution. So in example 3, what we want to do is find the volume of a solid formed by revolving the region bounded by this parabola, y equals x squared plus 1, y equals 0 here, which happens to be the x-axis, x equals 0, which happens to be the y-axis, and the line x equals 1. So let's go ahead and graph the parabola first. And the parabola has a vertex at 0, 1. Substitute 0 and you get 1. Substitute 1 in, 1 squared plus 1 is 2, so 1, 2. Reflect. Parabolas are always symmetrical about the y-axis, symmetrical about their axis of revolution. That's what I meant to say. And let me draw a little bit better parabola here on the left and clean this up a little bit. Okay, there we go. That looks a little bit better. Okay, highlight those points on the parabola there. And then we also want to graph the bounded region bounded by all of these lines. So we got y equals 0 here, the x-axis. X equals 0 happens to be the y-axis. And then we have x equals 1. Right here, x equals 1 is a vertical line through 1. Alright, and we're going to bound this region. The region bounded by all these functions happens to lie in here. And we need to revolve it around the y-axis. The y-axis is right here, so we want to, that's our axis of revolution. Alright, so what I'm going to do is kind of reflect this region around the y-axis here and reflect it across and draw the other side so you can see what it kind of looks like in 3 dimensions. So, oops, what's going on here? There we go. And what I'm going to do is draw the top portion of the solid. So it kind of looks like this. Right here, it looks like a cylinder with a dish, a hole that's shaped of a dish running through it. And the typical cross section is different depending on where you are in the solid. Let's take a look at that. Between 0 and 1, the cross section would look like a disc right here. And then from 1 to, let's say, 2, the cross section would look like a washer or a disc with a hole in it. These are called that's called the cross section. So what we're going to have to do is set this up using 2 integrals. One integral from 0 to 1, and then another integral from 1 to 2, using the disk method for the first integral from 0 to 1, and then the washer method from 1 to 2 because it's a disk with a hole in it. Alright, so let's take a look at what's happening here. From y equals 0 to y equals 1, it's a disk. So what we're going to have to do is figure out the radius, and the radius is the distance between the 2x values here, the radius. So in this case, the radius is 1. So my disk volume is going to be pi times radius squared times its thickness, which in this case is dy, or this thickness here, dy, the differential of y's. So pi times 1 squared times its thickness. And that's the integral for, or that's you're going to be used for setting up the integral from 0 to 1. Now from 1 to 2, something else is happening. So from y equals 1 to y equals 2, all right, it is a washer, the cross section that is. Okay, now because of that, our disk volume, or disk with a hole in it, or washer, is found by taking pi times big R squared, the outside radius, squared, minus little r squared, the inside radius, times its thickness. Now what is the big radius? Well, let's take a look at that. The big radius is right here, that's big R. Little r is right here. And that's going to be the difference, or this distance along the x-axis here. Big R is the distance between 0 and 1, so it's obviously 1. The question is, what's little r? Well, r here, this distance, is equal to, some difference between the x values, right minus left, and it's going to be whatever x is equal to in respect to the function of the parabola. So what I'm going to need to do is take my parabola here, y equals x squared plus 1. I'm going to have to solve for x. So I'm going to subtract 1, and then I'm going to square root, and that's my x value given any y value. So my little radius is actually equal to the square root of y plus 1, or excuse me, y minus 1. Okay, so here we go. I want to take big R squared, which is my outside radius, which is 1, squared, minus the inside radius squared, which is the root of y minus 1, squared, pi times that, and then times its thickness, which is dy. So all my integrals are going to be in respect to dy here. What is that going to give me? Well, it's going to give me pi times quantity 1 minus the quantity y minus 1 dy. Distributing through the minus sign, that's going to be equal to pi times the quantity 2 minus y dy. That's going to be my washer there from 1 to 2. So what I'm going to have to do to find the volume is set up an integral, first from 0 to 1, and integrate using my disk method here, which is going to be pi dy, plus my integral from 1 to 2, my washer, because my washers are going to be formed from y equals 1 to y equals 2, and that's going to be pi times the quantity 2 minus y dy. Okay, my first integral is going to give me pi y, and I have to evaluate from 0 to 1, plus pi times quantity 2y minus y squared divided by 2, evaluated from 1 to 2. Okay, and we just evaluate this. First integral gives me pi minus 0, which is just pi, or in other words, pi times quantity 1 minus 0, which is just pi, plus pi times 4 minus 2 minus pi times 2 minus a half. Okay, and when you evaluate this, you get pi plus 2 pi minus 2 pi. The 2 pi's are going to cancel out, plus another half pi, and that's going to give you 3 halves pi total, cubic units and all. Okay, so in this case, you have to be careful because the integrals, or you're going to have to find the volume by setting up two different integrals, both in respect to y, because we're revolving around a vertical axis of revolution. Okay, on the example 4, what we want to do is find the volume of a solid formed by revolving the region bounded by y equals the cube root of x and y equals x force, or x divided by 4, about the y-axis here. And I'm going to have to limit this to quadrant 1 only. So I've got to write that down. So quadrant 1. Okay, so the first step is to graph the function in first quadrant and find the bounding region first before you start revolving. And what we want to do is just take some x values, think real simple here. When x is 0, 1, and let's say 8, find some cubes and see what you get when you cube root them. Okay, so cube root of 0 is 0, cube root of 1 is 1, cube root of 8, okay, well that's 2. So you can plot those points there. So 0, 0, 1, 1, and then 8, comma 2, right here. Actually, you know what? Let's make it a little bit more pronounced. Let's change the scale on the y-axis here. Let's make this 1 and this 2. Okay, so 0, 0, and then 1, comma 1. So right 1, up 1, and then right 8, up 2. There you go. It's a little bit more pronounced. Okay, so the cube root function looks like this. So this is the cube root of x right here, and x force, let's set up a little table value here real quick. Y equals x divided by 4. 0, 1, 2, and 4, 8. So you get 0, 1/4, 1/2, 1, and 2. You plot those. 0, 0, 1 and 1/4. 1 comma 1/4 would be here, and 2 comma 1/2 here, 4 comma 1 here. It's linear, of course. So let's draw that line. There we go. And a little bit off right there. Let's change that. Okay. Because 8 comma 2 is here. Oh, my other point is off. Okay, so let me regraph my cube root function. I was one off on my points here. There we go. There we go. Okay, so you plot your points there. Go ahead and bound the region, shade in the bounded region here, and then you have to revolve it. Okay, now what we want to do is revolve this bounded region about the y-axis, and the y-axis is here, of course, and we want to wrap it around here. So what I want to do is kind of just sketch what it looks like on the other side in quadrant 2, because I got to revolve it around the y-axis. So this solid's going to be formed in quadrants 1 and 2. So let me just draw the function over here, just a portion of it, and draw the linear function over here, just a portion of it again. Oops, right about here. And again, the bounded region is going to be in here, reflected. That's just a sketch. And let's take a look at the typical cross section of this. Okay, so if I start here, so our washer is going to look like a washer or a disc with a hole in it, and the hole is going to be in through here, of course. There's going to be an opening there, and it's going to look like this solid form in figure 2. This would be cool. We'll call this figure 1. This is figure 2, and this is figure 3 down here. Okay, so when you wrap this around and revolve it around the y-axis, you're going to have a solid formed. And the inside's going to be curved, okay, and to find the volume of it from bottom to top, basically from 0 to 2, we're going to have to use the washer method because this is going to have a hole in it. So what I need to do is figure out the outer radius first, this distance right here. We'll call that big R, and then figure out the inner radius here, this distance here. It's going to be little r. What are those distances there? Little radius and big radius. Well, what I need to do is take each function here and solve for x, because this radius here is whatever this x value is. Well, so r equals x, and that's going to be equal to something. So I need to solve for x on both functions, both in the linear function and then also the cube root function. So I need to start working on that. Okay, and then, so what I'm going to do is I'm going to take my cube root function here, y equals the cube root of x, cube both sides to get y cubed equals x. And then I'm going to take my linear function y equals x divided by 4, and I'm going to solve for x simply by multiplying by 4. So x equals 4y. So my big radius here is found by taking a look at the x value on my linear function, and that's going to be equal to 4y. That's the big radius. The inner radius is found by looking at whatever x is on my cube root function, and that's going to be y cubed. So my little radius, r, is going to be equal to y cubed, and my big radius is going to be equal to 4y. So my washer volume for this particular cross-section, or disc volume or washer volume, remember a disc or washer is just a disc with a hole in it. It's going to be found by taking pi times big R squared, which is 4y squared, minus little r squared, which is y cubed squared, times how thick it is. Now the thickness is found right here. The difference in y values, or a differential of y, we'll call that dy. So times dy here. So my integrals are going to be in terms of y. I'm going to simplify that first. So my washer volume is going to be pi times 16y squared minus y to the 6th times the thickness dy. And that's the volume of one of my washers from bottom to top. Okay. So what I'm going to do now is find the total volume. We'll do it up here since I have a little bit more room. So volume total, okay, is equal to the integral from 0 to 2. Okay, this is my upper bound 2. How do I know that? Well, I know they intersect at this point right here, and that's at height 2. So my bounds are from 0 to 2. My washers start at y equals 0 and go all the way up to y equals 2. So from 0 to 2, of pi times 16y squared minus y to the 6th dy. Alright, so bring out the pi if you want. Integrate. We're going to have pi times 16y cubed divided by 3 minus y to the 7th divided by 7, evaluated from 0 to 2. And after you substitute 2 in, the final volume is going to be 512 pi divided by 21 after you do the arithmetic. Cubic units, of course. Okay? Alright, and let's try this one more time. On example number 5 here, I'm going to